Okay, thanks a lot for coming and listening to this talk that I entitled Nuclear Energy for the Planet. And I wanted to add in this slide all the institution, national lab and universities where I could study and work in the nuclear sector during my career. And before going into the discussions of why I think nuclear energies should be considered a clean energy source that can enable us to reach the much needed green energy transitions that we need to do by 2050, I think it will be useful to share with you the different nuclear fields, areas that I could work on and that enable me to let's say, collect all the information that are going to be shared with you today in this presentation. As an Italian, I always was convinced that nuclear was not a good energy source and that could not to be, and it was not good to be pursued. But I had the lack, curiosity and resilience to go and work in the nuclear field abroad. And I was working during my master's in the field of nuclear waste final disposal. I was working in Sweden, one of the two countries that I actually added here in this map. Finland and Sweden are the only two countries that I've finally decided of a permanent solution for encapsulating nuclear waste. I was working on the materials that we use to encapsulate safely nuclear waste that you can see here. In this case are the nuclear fuel rods coming out of a light water reactor. And I was therefore trying to investigate the long-term robustness of the materials that we use to shield waste in a repository. After this experience in Sweden, I was able to work at Imperial College London, where I pursued my PhD under supervision of Professor Billy in the Department of Materials. And the second, let's say, part of my studies focused on the fuel itself. And my PhD, it was quite interesting on the fact that I was working on fuel that was considered nuclear waste. But at the same time, at the conferences was where I was presenting work on this fuel that was coming from the 50s, and it was a non-oxide nuclear fuel. Many of the colleagues I was working with, they were presenting new and advanced manufacturing processes to build and manufacture the same fuel that can be used nowadays in advanced technologies and advanced generation reactors. So I was working on waste, but that it is considered fuel by some countries and with some technology that we have in our hands. Then I was able to work on the long-term operation of nuclear power plants, which is a really crucial part of the nuclear industry. And we will see how key is the extension of nuclear power plants concerning the provision of nuclear electricity and clean electricity in our market. What was interesting, thanks to the postdoc under supervision of Mark Wenman at Imperial College London, was that we were investigating the problem of life extension and how we can extend the life of nuclear power plants, together with novel techniques that we can apply nowadays on steel that is made the pressure vessel, that it is actually the only component that has to be robust and sound for life extension. We can work on advanced technology, advanced manufacturing techniques that can enable the realization of small modular reactors, for example, so a newly generation power plant. So it was interesting to apply old and traditional technology on novel manufacturing techniques. After I was focusing my efforts and learning experience on nuclear fusion. So I was able to get a Fusion engineering grant for the realization of nuclear fusion as a possible source of energy, because obviously fusion is interesting and very important technology that has received a lot of attention in the past years. And as a material scientist, I was able to apply the knowledge from 60-year plus operation of nuclear fission power plants to the realization of fusion reactors, because we will see briefly, but many of the aspects of the current generation nuclear power plant fleet, like the light water reactors that we have nowadays in operation, and the technological advancement of the advanced generation fission power plants, actually have a lot of synergy and can benefit the realization of fusion reactors, because many of the aspects from a reactor point of view of fission power plant are to be applied in future fusion reactors. The challenge, though, of fusion is that we also have some peculiar phenomena that we cannot study directly in fission reactors. So there are some challenges that are yet to be solved in the fusion reactor world, but it is a promising technology. Though the two technology, even though are very different from a nuclear perspective, in a sense that fission, as I can show here, relies on the splitting of a heavy atom by impact of a neutron with the release of energy and energetic particles. Fusion itself is very different from a nuclear perspective on the fact that we intend to fuse, push together some really light atoms. Though the way we want to use these two nuclear technology to produce energy and electricity is quite similar, in a sense that both fission and fusion, after, of course, when the reaction occurs, produces neutrons, highly energetic neutrons, and highly energetic particles. And we want to heat fluids through these nuclear reactions to then produce electricity. So this is why the synergy from a reactor point of view perspective are really similar. Here is a picture of a natural fission reactors, and here is a picture of one of our most famous natural fusion reactors, because of course we know that nuclear fusion happens in stars, and all of the atoms, most of the atoms we are made of, the planet is made of, apart from hydrogen, actually are coming from the nuclear fusion reactions. If nuclear fusion happens in stars and we are trying to make it happening on Earth, fission has happened naturally on Earth billions of years ago. And here is a picture of a natural fission reactor, which is Oklo. And we have observed how fission can be working in reality, like naturally, and how we can exploit. So if both of them are really powerful energy sources so far, we have to rely on fission for the electricity and energy production. And fusion reactors here are promising, but they are many decades away to be a proven technology for energy source. So I'm here to talk about nuclear with a focus on nuclear fission, because I believe that what we're currently facing, it's a climate emergency. And if we look at the data and the science, we know that if we continue to use fossil fuel for our energy and electricity production, we may undergo irreversible processes, and the world may not really be able to recover. So if we look at the data and the science, we see that during the past 50, 70 years, the CO2 emissions have risen a lot. And what the scientists tell us is that we do not only need to reduce or stop to emit CO2, but we have to enhance or increase the energy and electricity needs while reducing the CO2 emissions, which is something that I think is underestimated. So here you can see the NASA data and the current level of CO2 emissions. And what we need to do is drastically reduce it while at the same time allowing a sustainable development for all. Because if we are, I must say, I think we are lucky because we live anyway in some countries that enable us to live in a very comfortable way of living. We need to remember that many people in this world do not have access to energy, clean energy or clean electricity, as you can see here by this map showing you the density, population density. So if we were really to address the issues of climate change while enabling a sustainable development for all, we understand that the need for a large amount of electricity and energy by clean technologies is going to be a massive request. So what we have in our hands nowadays are mainly these 4 technologies that are considered clean or low carbon. Here on the left, I've added a picture of a nuclear reactor, a fission reactor, a hydropower, wind, and solar. And I wanted to include these pictures just for you to see that no electricity source is completely perfect or completely clean. Because if you look at these images, you will see that all of the technologies that we have in our hands require minerals, mining, materials. They have an impact on land, an impact on the environment. So if we look at the data, we cannot simply disregard one technology compared to the others. We have to put them all at the same level. And here now we can discuss on the peculiarities of nuclear and hydro and how these 2 constant sources of electricity can really help the realization of the provision of clean electricity for the next years and decades. By simply comparing all the electricity sources, if we think about having the need to decarbonize the electricity, the transport, we will see that there will be a major request of minerals for all the technologies that we have in our hands. And here you can see the data from the International Energy Agency that show you how much minerals are required for the clean transition. Here are the minerals required for electrifying transport, and here are the minerals required to electrify the electricity sector. And you can see here the kilograms per megawatt, so the energy installed. But if I was here to plot, and I should have probably, if I was here to plot the kilograms of materials required for electricity produced, then you will see that wind and solar requires a large amount of materials just because of their intermittency. So you can see that nuclear actually fits quite well in terms of like reducing the amount of crucial minerals that we need to produce clean electricity. And we should not forget what we're facing in the current situation, which is very crucial and really bad in terms of like the situation that is related on gas supply. If we were to look at where are the major electricity processing sources to produce batteries or solar panel, again, the geopolitical situation can be a really crucial factor that we need to add in our equation. So here is again the graph from the International Energy Agency, and you can see where are the countries that have the technology in their hands to produce materials, process materials for enabling battery production, wind, magnets for wind power, and mineral minerals that are used in solar panels. Nuclear has some mineral requirements as well, like chromium, for example, nickel, but the fuel itself, uranium, is quite homogeneously dispersed in many of the countries in the world. So we have to add also these crucial, important aspects in our equation, I think. And I have been talking a lot about electricity because we urge to decarbonize our electricity sector. And I've added here a picture that should clearly show you where we use our electricity. Though we do not need to forget that to really decarbonize and reduce our CO2 emission, we need to focus on decarbonizing industry, that I've added here picture, and transport. We have seen some data on transport, electrifying transport and the mineral requirements for batteries, but we also need to think how we charge our batteries. So of course we need a large amount of electricity, but the industry itself, for decarbonizing industry, instead, we do not only need electricity, we often need really hot fluid that can enable processes, industrial processes such as metallurgy and production of steel, ammonia production, hydrogen production. So it is important to focus our efforts on electricity, but we should not forget that other 40% of our CO2 emissions actually comes from transport and industry. And the jump in terms of today's situation and 2050 situation is gigantic. Here I've added this graph that shows that just by looking at electricity, today 70% of electricity comes from fossil fuel, and by 2050 90% should be produced by clean energy. So we have hydropower, solar, wind, and we can also use nuclear to decarbonize the electricity sector. But as mentioned earlier, we need clean heat, and nuclear is a really good technology to produce heat, because nuclear, compared to all other clean energy sources, produces hot fluid that then are converted into electricity with a roughly 30% efficiency. But first of all, we heat fluids, and these fluids can be used directly to decarbonize industry or producing some crucial energy vectors like hydrogen, for example. And I wanted to add it here that when we talk about transportation, we should acknowledge the fact that nuclear reactors are being used already to decarbonize or anyway serve as a nuclear, as a reactor propellant for marine transport. And marine transport is also a field that has to be decarbonized in the next decades. Here is a picture of an icebreaker, and we have many examples of ships being propelled by nuclear reactors. Considering all the technologies that have been really improved in the last decades, though we should acknowledge the fact that nuclear reactors is the technology that is still being considered as the safe and constant and reliable electricity and energy source for really highly technological missions such as Mars or space missions. So I've added here the fact that NASA is reconsidering nuclear reactors as a propulsion for space missions, because we know that is a really constant and reliable energy source. And if I have to mention nuclear and its role for energy transition, I wanted also, though, to mention the use of nuclear in nuclear medicine, because nuclear reactors itself are used nowadays to produce some really important radioisotopes that are used in hospitals worldwide for the cure of many and several diseases. So nuclear is also being used for the health and benefit of society in the medicine world. But let's go back to the energy and electricity problem that we're facing. So we are constantly stressed by the urgency of having to ensure clean, safe, and affordable energy to everyone and clean electricity. And if we look at the data, nuclear is already providing 30% of the clean electricity worldwide. So it is already a large amount of the clean electricity used in the world. And by looking at the data, if we compare all the different electricity and energy sources, we can see the actually nuclear energy together with hydropower and wind and solar are all of them really comparable in terms of safety and clean provision of clean electricity. And we're talking here about low carbon electricity. And here you can see data that are available and that can be used, I think, to compare all the different energy sources. And if we look at the countries that have been, let's say, have put an effort on keeping the nuclear fleet, we can see that if we have nuclear together with renewables, it is already a good and proven technology for limit CO2 emissions. Here is a typical map that you can browse on electricity map. And green means countries that are low carbon, have a low carbon electricity mix. And you can check, but all of the countries that are able to provide low carbon electricities are the countries that either use hydropower or nuclear together with renewables. Sweden have large share of nuclear. Norway has a large share of hydro, but not every country is able to have a lot of hydropower, while nuclear can be installed in any country. Here, France is not as dark green as Sweden, just because some of their reactors are now currently in shutdown. But France as well has always continue to invest in nuclear and is a proven solution, can be a proven, let's say, energy mix. What is critical and important to consider about nuclear power and hydropower is that they can be used as a constant and reliable source of electricity. They can operate, and nuclear can operate 24 hours a day, 7 days a week, and can really provide the electricity that we have to have constantly every day throughout our day. Because if you compare the intermittency of all electricity sources, you can see that wind and solar are not always available, and we need something that can back them up when the sun is not shining and the wind is not blowing. And we know that the fluctuation of electricity demand is not always constant, is true. And so far, nuclear has been used as a constant share of our electricity needs. Here it is depicted in green. It's normally used as a constant source of electricity. And if we consider that the electricity share will rise in the next decade, we will anyway need more of this share of electricity being constantly supplied by a electricity source. And this electricity source can well be a nuclear power plant. But with the increase of renewables and intermittency of our renewables, we also have to have some electricity plants that can back up renewables. And we know that gas has been used for that, but hydropower can be used for that. And nuclear power plants actually have been using in a load following option. So here you can see the way how also nuclear power plant can be, let's say, operated to follow the load, even though it is the main aspect of nuclear is that it's a really stable electricity source. If we were to compare also the land requirements. A good and positive aspect about nuclear is definitely the small land required. So here you can see the comparison between nuclear and solar and wind for electricity produced. So we can maximize or actually minimize the land requirement by adding all of the sources together. And obviously, in the equation of our, let's say, good energy strategy, we should definitely need to consider costs. And I wanted to share with you this graph, which is available online. It is from 2020. So the cost of electricity here actually does not consider the skyrocketing prices of gas that we are facing with the current gas prices. But anyway, even without considering the gas increase in the prices, where is nuclear sitting compared to all other technologies? Here is the price per megawatt hour, so per electricity produced. And nuclear sits here. It's very well aligned with all other technologies, both low carbon technologies and fossil fuel technology. But what is striking here is that one voice of nuclear, which is nuclear LTO, that stands for long-term operation, actually is the cheapest source of electricity on the market now. And I have mentioned LTO at the beginning of the talk, because what is LTO? It's basically the extension of the life of the nuclear power plants, because power plants that were designed to operate for 40 years have been proven to be safe and sound to operate for other 20 years. So many of the nuclear power plants nowadays received an okay from the authority to operate for 60 years. We're now discussing about operating these plants for 80 years, and the Director General of the International Atomic Energy Agency had mentioned that they may well operate for 100 years. That means that by increasing the life of a reactor that is already being built, the price of electricity it's very cheap, because one thing about nuclear is that most of the costs are related to construct the building and the power plant. The fuel itself is not impacting at all or very little on the final cost of the electricity production. Though I have to acknowledge in this talk the fact that nuclear has been a declining technology for the past 30 years in the Western country. It wouldn't be fair if I was omitting this. We have been stopping build reactors for many decades in both US, UK, and Europe. But and many of the issues that we're facing now that you can read on the news and you can read on the reports are definitely an increasing time we use to construct buildings and the increasing costs. But I think this analysis made by Frédéric Jobert, Boston Consulting Group, is quite interesting, because they have tracked the amount of time and the amount of power plants. So here you can see these numbers are the number of reactors being built, and here the time needed to construct those buildings in the Western countries, for example, US and France, and in the Eastern countries, Korea, South Korea, and China. Well, if we were to compare the West and Eastern approach, now we can see that in the Western country, after Chernobyl, basically we stopped building nuclear power plants. We stopped having a supply chain competence, and you can see that by decreasing the number of reactors, the time needed to build a reactor increased, just because we didn't have a supply chain, an efficient supply chain. So here you can see that we were only building a few power plants, and we needed quite a long time to build them. However, if we compare the approach on South Korea, for example, they are steadily building nuclear power plants, and the amount and the time that they need to construct a power plant is much shorter. In 7 years, 8 years, they are able to build a nuclear power plant and operate a nuclear power plant. But yes, it's true. We have to go back on track and enable the construction on time and on budget to be very competitive, like we were in the 70s. And of course, I should not avoid talking about nuclear accident, because obviously public acceptance and safety is key in the nuclear sectors, and has to be and is being pretty much considered in the current generation of nuclear power plants, because nuclear has always been evolving and learning from lessons learned and accidents that have occurred in the past. So I need to include here what happens, and here I added the 3 main accidents that we have seen in the production of electricity, and it is 3 Mile Island, Chernobyl, and Fukushima. And if we look at the data, and I wanted to include here the data, we can see that on the 2, let's say, accidents that are here depicted, the 3 Mile Island and Fukushima, actually, if we look at the data, and you can read them in the United Nations report, no injuries or death are related to the operation and the accident of the nuclear power plant. And I have to stress on the fact that Fukushima, which is the latest and last accident occurring in 2011, the nuclear power plant was built in the 70s. It was a design from the 60s, and it survived a 20 meters of tsunami and a 9.2 earthquake. And whilst the nuclear power plant remained intact, 20,000 people were completely, swept away by the tsunami. But I should acknowledge the fact that, yes, we had a chemical reaction, we had the hydrogen explosion, and we have now included in all the current nuclear power plant fleet some systems, an additional safety system that should enable us to never have again another Fukushima. If I was to talk about Chernobyl, it was a definitely bad accident, and I must say a badly managed accident. And yes, there have been, unfortunately, a consequence on health and on the people that were there to solve what has been induced, I must say, issues on the plant. But I urge you to go and look at other type of accidents in the electricity sectors or in any other sectors. If we go and look at the history of incidents of other electricity sources, fertilizers explosion, hydropower dam, I didn't want here to list all the accidents, but I urge you to go and look for yourself and try to compare the data with your perception about dangers and risks, because I believe that you have a worse perception on nuclear risks compared to the data you will read. And going forward towards understanding why nuclear is still a very controversial energy source, I have to talk about nuclear waste, because most of the people I talk to are actually worried and are questioning where we put in our nuclear waste. Well, nuclear waste has been produced, is being produced, and is being stored in many different repositories. We mentioned at the beginning of the talk, some countries have a permanent solution, they believe, so we will dispose our waste in geological repository. But in the meantime, all other countries have been storing their nuclear waste in facilities. And you can visit these facilities where you will see that even the, let's say, most radioactive nuclear waste, which is the high-level waste, the spent fuel or even spent fuel being recycled and separated, is encapsulated, is shielded, And you can go and see for yourself and visit those buildings that host these nuclear waste. And in terms of volume, the UK have estimated that for all the waste being produced and for the next production up to 2125, well, all the nuclear waste anyway, the volume can fit in a stadium. So it's definitely is something that we are taking care of. And I should not forget to mention what are the technologies that we have in our hands, because if most of the fuel that comes out of the reactor now is considered waste, as I mentioned at the beginning of the talk, then yes, after the usage of the uranium in a light water reactor, there's still an option, and we have this option from the 50s that could be recycling and increase the sustainability of nuclear by reusing uranium, plutonium being produced in a light water reactor to produce new electricity and energy in a fast reactor. And I included here two pictures of the latest generation of light water reactors, all kilowatt in Finland, and the sodium fast reactor that is being connected to the grid. And the fuel itself, after recycling or reusage in a fast reactor, anyway, have a shorter lifetime and therefore can be encapsulated for shorter time compared to what we are usually worrying on if we think about just throwing away all the fuel coming out of a light water reactor. So I think last point to discuss when talking about nuclear and what is the technology that we have nowadays, I should also talk about the really last stage of nuclear power plants, which is the decommissioning stage. Because as a first-hand experience, we were working as decommissioning engineers in a nuclear power plant design stage that at the end never got built or never got the permission to be built. And I think I want to share with you this information. Like, nuclear industry is one of the only industry that actually have to consider the dismantling, decommissioning from the design stage, so that at the end of the operation of a nuclear power plant, that, keep in mind, it is considered 40 years, but may well be 60, 80, or in the future, 100 years. We have to ensure that we will leave the field occupied by the nuclear power plant and return it to a green field, so completely intact, without any sign of the presence of the nuclear power plant. So I think this is something to share with the people. Like, nuclear industry have all these requirements already considered at the design stage. So I wanted to, I added here this picture just because I think nuclear should be considered a really clean technology and an ally for our clean energy transition. But I must admit, maybe this picture may be too biased, so I will leave you with these 4 images because they just represent objectively what we have in our hands today. So we have the fleet, the light water reactors fleet, or gas fleet that is, being built in the 70s, 80s, and is being operating well for the past 60 years. We are now building the novel generation evolutionary reactors, like water reactors. This is all kilowatt that has reached criticality this year. And I should mention here 2 reactors that have the technology of the so-called generation 4 reactors, and they promise to either serve the industry well. This is the high temperature pebble bed reactor in China that will enable to use really hot fluid up to 700 degrees C to decarbonize and industrial sectors. And here is the sodium fast reactors that can enable a recycling and reusage of nuclear waste into new nuclear fuel. And yeah, with this, I'd like to leave you with these images. I'd like to thank you a lot for listening to me, and I will be very happy to take any question you might have. Thanks a lot. So yeah, I guess if you don't have any question or curiosity, we should maybe wrap up, Louise, or?
Yeah, if there are no questions, which it doesn't look like there are, then yeah, feel free to wrap up.
Okay, so well, thank you very much. And well, I don't know if I have any questions. I am yeah, I'm an academic visitor, so I have still my imperial email. And yeah, thank you. Bye bye.